Hello everybody. I'm making this video as a result of a discussion that we were having on the Big Clive live stream, which happens over on Twitch. I'll stick a link in the description in case anyone finds my video and would be interested in joining us on the live stream. They usually happen every Saturday at 9 PM UK time. But I suspect a lot of people who watch my videos are finding them originally through Clive, but that's beside the point. Anyway, we were discussing earthing arrangements and pen faults and diverted neutral currents and so on last week, and that's quite a complicated thing to explain in text, so I figured I would make a video explaining with diagrams and demonstrations how it actually works, because it's much easier to show rather than explain via text. Anyway, so this video is going to cover basically what earthing systems are, the differences between them, what a diverted neutral current is, what a pen fault is, how to detect them, why they're dangerous, that sort of thing. So getting straight into this, there are 5 earthing systems that we use in the UK. This is UK specific, I should say that. There are 5, those being TNC-S, TNS, TT, IT and TNC. IT and TNC are weird and not really used much in, well, not used much at all outside of some extremely narrow applications. I will explain more in a second, but the 3 main ones, TNC-S, TNS and TT, are the ones we'll be talking about today because they are most relevant. In your house, the cable which comes from the substation into your house is terminated into a thing known as a service head. Ideally I would have one to show you, but I couldn't get one on short notice, and yes, so next best thing is a diagram, which I have here. There are 2 main types of service head you will find. This one is used for TT and TNCS, and this one is used for anything really, but mostly for TNS applications. The incoming cable at the bottom here is the one that comes from the substation. Modern cables that they use for this are known as concentric, which is where they're a bit like a TV aerial cable. They have a core in the middle, which is usually aluminium, 60mm squared in most applications, and then around the outside, a bit like a steel wire armour, they have copper strands, which are the neutral connection, so the live in the middle with the neutral wrapped around it. The neutral gets taken off to the side and put into the neutral terminal, which is a solid block here, and the live goes into the terminal for the fuse, which then goes out to your electricity meter out the top here. The TNCS, which is earth neutral connected separate, so you can see this solid block here, the earth comes out, that connects back to the neutral, which goes back to the substation. In the TNS application, they use a similar cable with a slight difference. It's called split concentric. So the same, you have a 60mm, usually aluminium, cable in the middle for the live, and then around the outside you still have small wires, but half of them are insulated and the neutral, and half of them are bare for the earth. So you have your live comes in through the fuse and out to the electricity meter, the neutral goes into a solid neutral block here and then out again, and the earth comes into a separate earth terminal on the side and goes out to your thing. Some of them are so-called adaptable service heads, so they have a link you can install here, so it makes it basically into this TNCS, and on a TT application they would use this service head, but they just block off that hole at the side, so you have a live and neutral come out and no earth provided by the network operator. With this anatomy of a service head out of the way, I will get my other diagrams and I'll show you the sort of schematics of the earthing arrangements, which will make it a bit clearer what's going on. So here are my schematics. These 3 here are the main ones that are used for domestic commercial applications. These ones on the side are the weird ones that I will explain in a second. So first one we have is TNC-S. This is by far the most common earthing system in the UK, and it is also the most dangerous and I would argue the stupidest, and I will, because of the pen fault issues, but We'll get onto that in a second. But what happens is you have your transformer where the 11 kV comes in. The secondary winding is earthed by the supplier at the transformer. There is then a conductor which comes out here, which is called the pen, up to that point there where the earth splits off, which is protective earth neutral combined, and the live comes out here. So we take the pen up in the service head, we split the earth off out it, and then we have a neutral, which is why we have, so T stands for terra, which is earth. So earth, neutral, connected here, and then separated at the load. This, I say, is the most common one. It has issues, we'll get onto that in a second. We then have TNS, which is earth, neutral, separate. So again, 11 kV comes in here, we have the secondary winding. Live goes off, neutral goes off. The neutral is earthed by the supplier here, but there is then a separate earth which goes from here to the load. This is the best option, but they got rid of it because of the additional expense, where you were running 3 cables rather than 2. And then finally we have what I would say is the best compromise now due to RCDs, which is TT, standing for earth to earth, terra terra. So the supplier have their transformer, 11 kV comes in, secondary winding here, they earth the neutral at the transformer, they then give you a live and a neutral, nothing else. You have your own earth electrode which provides the local earth for your installation. These are the 3 most common ones. These other ones you will probably never come across unless you're doing something very, very weird. We have TNC. TNC is for terra neutral connected. That is where you have the transformer, live, and then pen rather than neutral because it's the protective earth neutral combined, which is earth referenced. There is a section in BS 7671 about this. I cannot think of any application where you would ever use it for anything, because in order to, so this falls under the Electricity Safety Continuity and Quality Supply Act regulations or whatever it is, but in order to run a TNC system, I'm pretty sure you need a license from the Home Office, but it is in BS 7671, it is a thing that is mostly for distribution network operators though, or DNO. I should explain that. DNO is the person who owns the substations and the cabling between the substations and the service head. We then have IT, which I've drawn twice because there are 2 variations of it. It can either stand for impedance to earth or isolated from earth. This one here is the most common application of it. So on all high voltage distribution in the UK, it is IT earthed. That means you have the 3 phases in a star point on the secondary like this. The point from the middle goes through the NER, neutral earthing resistor, down to earth. That means that your earth current or your earth fault current is limited by this resistor. So on all high voltage transmission lines in the UK, ranging from 11 kV right up to 400 kV, as I understand it, are current limited to a maximum earth fault current of 1000 amps by the neutral earthing resistor. You would take a neutral from that point too if you wanted to use it, but they don't have neutrals on the high voltage for UK stuff. But that's why it's in brackets. If you used an IT system like this though, for a 230, 400 volt or whatever, it would have a neutral coming from there. The other option is terra neutral isolate, or sorry, earth isolated, which is again we have the 11 kV, the secondary is not earthed at all, so we have a live and a neutral which come out. They're actually, I'm not sure how you'd term them both, because it's not really a neutral because it's not at earth potential, but you have a live and neutral coming out, and you then have an earth which is provided separately, and the live is not referenced to the earth, so their voltage between them is not tied. The IT system, the only place I can think of it being used is in operating rooms in hospitals. Other than that, I can't think of anywhere you would actually see it. So these are the 3 ones we will be focusing on today. The issue I was going to get into now is the problem of pen faults. and how pen faults can be really, really dangerous, because it can result in all of the earth metalwork in the installation basically becoming live. And they can also result in fires because of a phenomenon known as a diverted neutral current. I will get another diagram now to try and explain how a diverted neutral current works. So, we have a crude drawing of a street. At this end we have the substation, which feeds the pen out the bottom and the live out the top. And then each of the houses has a neutral and a phase going to it with a TNC-S earth. And this here is a gas main or a water main or some utility pipe. What has happened in this place though is, unfortunately, the pen conductor has broken partway along the street here. Now, what happens? So the load current goes in the first house, out the live, up, through the load, back down the neutral, back to the substation. That's fine, that's working as it's supposed to. In the next house, it comes along, up the live, through the load, down the neutral, and it can't get back because it's broken. So what will happen is, it will come up the live, it will go through the load here, down, through the neutral earth link in the service head, down the bonding cable, into the water main or gas main, through the pipe, back up the bond cable on the main in another building, through the link and down to neutral. And the same thing will happen with all of these houses here. So what will end up happening is this water main, or gas main, or whatever it is, will end up carrying the full neutral current of the entire street. Or multiple houses. It depends on exactly where the break happens and things like that. But obviously a pipe is not designed to carry current, so they will get hot, they can go on fire. There have been fires and explosions from gas mains, and it's not good. In the US, I think they even have issues with the screen on cable TV sometimes, because they earth that at all the properties, taking diverted neutral currents through it. And this is the problem, because you're ending up with, in some cases, substantial neutral currents flowing through things that are never actually intended to carry a current at all, let alone potentially tens or hundreds of amps. The other potential failure mode is if there is no gas or water or some conductive path for the neutral current to divert via. What will happen is, it will not be able to return to the transformer, so you will end up with this terminal here being live with reference to the actual earth. Therefore your earth is live reference to the actual earth. So if you have, for example, a electric car charger and you plug your car into the car charger, the bodywork of the car, the chassis ground of the car, is connected to the electrical earth of the charger. So if the pen gets broken or disconnected out with your installation, what will happen is the bodywork of your car will become live with reference to the actual ground. So if you then walk up and touch the bodywork of your car, you could potentially get a fatal electric shock from the body of your car to the earth that you're standing on. Which is why all electric car chargers in the UK now are either earth-free or have a pen fault protection device inside them. I'll get on to talk a bit more about what a pen fault protection device actually is and how to mitigate them. But I will first explain how these happen, because this is not something you would expect would happen, and it hadn't been an issue and then suddenly has now become a fairly serious issue for us in the UK. So how did this happen? I will explain in a second. So why has this become a problem now? Well, the answer is these things. Switch mode power supplies are the cause of basically all of this. You might be wondering, how is a switch mode power supply responsible for causing fires and electrocutions and the breaking of a conductor out with your installation? Well, I'll put this out of the way. The reason for that is because of a phenomenon known as DC electrocorrosion, which is basically where a DC leakage current flowing from a metal into a liquid will cause part of that metal to be pulled off and dissolved into the liquid as a metal salt. So you will result then in the metal over time being eaten away. And if it's not so much of an issue with concentrics, but it means, for example, if you have a link box in the street, which is where you have a joint in the cable, if that gets flooded with water over a long time, over months and years, the DC electric corrosion between the earth leakage from all the switch mode power supplies that are connected to the transformer will leak through the neutral earth combined into the water and into the ground, and over time they will eat away at that conductor until eventually it breaks and there's nothing left, or it will melt from the high current going through it and break, and you have now lost your pen. The other major cause of this has been a type of cable that was very commonly used called PILC, which is paper insulated lead cable, which is similar to the concentric, where you'd have the cores in the middle and then a lead outer around them, with the cores being insulated in a paper impregnated with oil, it used to be. But over years of these cables being egregiously overloaded, so for example the cable feeding our house here is about 4 millimeters squared and it's got 100 amp fuse on it. So passing 100 amps through a 4mm cable, you're going to get it fairly hot. And over time the oil in the cable, because a lot of these cables had been installed in like 1910, 1920, so even back in the 1890s, these cables will eventually, all the oil will evaporate out of them, and you have then dry paper inside, which is not an issue because it's sealed in lead. But with the DC electric corrosion that happens, the outer of the cable is connected to the combined neutral earth, or just the earth, depending if it's TNS or TNC-S. But it will dissolve the lead, and eventually you will get a pinhole in the lead, which allows water in, which will wet the paper inside, and can cause the cable to explode. It can cause the cable to explode and short out and trip, or it can just cause the cable to get mushy and wet. And what happens when the neutral earth combined conductor gets wet? Well, it dissolves. And again, over time, over months and years of this, the cable being wet and moist and dissolving and being eaten away, eventually the neutral current will be high enough to melt it, break, and you've lost your pen again. So that is I would say the cause of why this is such an issue now. And thank you very much for the cable jointer with Southern Power Distribution Networks who pointed this out to me. I was speaking to him a few years ago when I was out walking around Stirling. Met him, he was standing around a hole looking annoyed, so I went over and struck up a conversation, as you do, and he informed me of this, the problem they were having with the neutral earth pen conductors being dissolved by DC electric corrosion. So this is why it's a problem. Now, what can we do about it? Well, I'll get on to that now. So, there are probably a few things people are either thinking or typing in the comments right now, going, this isn't a problem because. I will quickly dispel those now. The first one is, this isn't a problem because the RCD will trip. The RCD will not trip. I will show you why now. So, here we have a circuit with the live, the pen, the earth, and a load resistor. This here is where your RCD will go. Your RCD only cares about whether the current going up here is the same as the current coming down here. So the current comes up the phase, through that, it goes through the load, back down the neutral, the RCD sees no imbalance, then, see, it diverts here and goes down to earth. That is why the RCD will not see the imbalance, because the leakage to earth happens after the RCD is checking it happened here. If it happened here, the RCD would trip, but not here. The other thing people will be going is, oh well, if you put an earth rod on the earth connected to the main earth terminal, that will fix it, because all the current will then go down the earth rod to earth and you'll get no dangerous voltages. But again, that's not true because of this here. The earth rod will have an impedance, 150 ohms is about average. It can often be much higher than that, sometimes it's lower, it depends on the conditions at the time. But we will say, for example, a 17 ohm kettle heating element, that will be passing 13 amps. If we look at the path the current will take, it will go up the live, through the kettle element, back down the neutral, it will come into the service head, through that link, and then try to go down to earth through your earth rod. Your earth rod, let's say, has 150 ohm impedance, so we are putting a 17 ohm resistor in series with a 150 ohm resistor. We now have a voltage divider. So using this formula of the output voltage is equal to the input voltage times R2, which is this one here, divided by R1 plus R2. That gives us 230 times 150 divided by 17 plus 150, which gives us an output voltage of 206 volts. So that means that this point here will be 206 volts above the actual earth. 206 volts is still more than enough to kill you if you touch it, so an earth rod will not fix the problem. Also, the earth rod will not make the RCD trip, because the RCD, as I said, will be measuring the imbalance between this conductor and this conductor. It does not care that the leakage is now happening after that, because the short to earth is after where the RCD is checking. The other thing I want to make clear is that this can affect all TN earthing installations. So even if your customer's installation is a TN-S installation, you still should check main protective bonding conductor currents and main earth currents before you do any work. Because if, let's say, their neighbour has a TNC-S earth and they lose their pen, the earth or the neutral current could divert via a water main or a structural steel part of the building or something like that. It could divert through the load down through the main earth into a bonding cable into some metallic bonded part, down your customer's bonding cable through their main earth, and then back to the substation via their TN-S earth. So you need to check that the protective bonding conductor current is 0 and that the main earth current is low. It won't probably be 0, but it should be very, very low. If it is significant, sort of more than 30 or 40 milliamps, you should immediately stop work. And in the UK, if you phone the phone number 105105, that will put you in touch with your distribution network operator in whatever part of the country you are in. So you can phone up 105, you tell them, I think I have a broken pen, I've got a protective bonding conductor current of 10 amps or whatever, and they will send somebody out to have a look at it. You can measure the protective bonding conductor currents with a current clamp meter, which I do have but not on my bench at the moment. 1 second, I will go grab it. So this is a current clamp meter. The way it works is you open the clamp up, you put your conductor through the middle there, you set it to the appropriate AC amps range, and it will tell you on the screen how much current is flowing through the conductor, which is in the clamp. You can also use it to measure leakage. This one is not a leakage clamp. I would say you should get a leakage clamp if you want to measure leakage. But the way you do that is you put the conductors you want to tell what is leaking from, all of them through here, and it will tell you what the current that is flowing up and not back is, which is the same way an RCD works. Actually, it has a current sensing coil like this, and it tells the difference between the current flowing up the live and back the neutral. I am now going to mock up a little demonstration to prove what I was saying here about RCDs not tripping and so on, and to demonstrate how it will work. So let me go get that set up quickly. So this is my setup here. It is a bit of a rat's nest, but I will explain what we have. The quick connect here is my pseudo grid supply. I have, coming from the neutral here because I don't want to trip the RCDs in the house, my pen, pseudo pen, and this is my basically diverted neutral alternative path. This white one is the functional earth for the RCBO, because that's what I had on hand. This is basically just an RCD but with a overcurrent protection rating on it too. So this RCD has the feed coming from the grid in, it has its neutral from the main earth terminal here, coming out here goes into this, into the input neutral for this. It has its incoming live, and then the outgoing from that goes to my load, which is this 150 watt light bulb. When I then power this on, to prove to you that the RCD does actually work, I will press the test button, and see, it does indeed trip. So this RCD does work. What I'm now going to do is I will disconnect my pen from the main earth. So we now have a broken pen. If I pop this out here, I should have said at the beginning, I'm an electrician, I care what I'm doing, don't replicate stupid live experiments like this. It's dangerous to mess with mains electricity. Anyway, so now we have no neutral. The neutral current will be going back via the alternative neutral diverted path. So I will reset the RCD, and as you can see, it is not tripping, even though the neutral pen conductor pseudo thing is not actually connected. All of the power is currently going via my bonding cable back to the substation through an alternative path. I will turn that off because I don't want to burn my bench. So we have the same setup as before, essentially. What I've got now is I have my current clamp meter, so I can show you the leakage that is being measured by the RCD. If I set this to 6 amps non-contact current, and I will put that around just one of the terminals. What's that light bulb touching? It's not going to burn anything. Good. This is awkward because I need to show you the screen. There we go. If I then turn this on, you can see we have just under 600 milliamps flowing. If I then put both of these around, this is with the pen connected, so the leakage it is measuring is 17 milliamps, which is obviously not true. That's because it's being interfered with by the neutral. If I move this, it probably will, yeah, it goes down. So the leakage is effectively 0. This meter gets confused if you have other current carrying conductors nearby. If I then disconnect the pen from the main earth again, so here it is, disconnected, and I power this back on and we put the current clamp back around, it is measuring, see, 3 milliamps, 5 milliamps. It's still picking up noise from other things, but it measures no leakage, even though if I get it off of there, I bring this in, my diverted neutral path, put that through, and you can't make that out, so we'll cover this. 600 milliamps. There we go. So that proves it. Even with an RCD, it will not trip if the pen breaks, because there is no leakage. The leakage to earth happens in the head terminal here. So, now I've shown why it's dangerous and why some of the things people think will work don't. What can we actually do to protect ourselves and our customers against this kind of issue? There are really only 2 good options. One is we fit a pen fault relay, which is a very expensive, very complicated box of magic that will use voltage sensing to detect when the pen conductor breaks, and it will then disconnect all conductors, so live, neutral and earth. This is the only time when an earth is actually switched, at least in the UK. You get ones that do all 3 phases too. Some of them use transformers to make a pseudo earth reference. They do all sorts of things like that. So that's one option. The other option, which I would say is better, is just don't use TNC-S. If it's available, use TNS, or just use TT, because now we have RCDs. TT is really, it's safer than TNC-S is. The high impedance of the earth rod does not really matter, because the RCD will trip with even a very low leakage. So that is really the only 2 good options. There are a couple of other things you can do which help. You can add galvanic isolation to utilities. So you'll get, say, a gas meter, you put a galvanic isolator which stops the current being able to flow through the gas pipes. You can do the same thing with water, or use plastic water pipes. If you don't have a galvanic isolator, you should check before you do it, measure continuity between the supplier side of the gas meter and your side of the gas meter. But if there is continuity between them, so your metal gas pipes inside your house are connected to the metal gas pipes in the street, you could put a jumper between your side of the gas meter and the suppliers, so any current that does flow will flow through that bond rather than the majority of it going through the flexible tails on the gas meter, because that can cause fires. And yeah, I'm trying to think if there's anything else. There isn't really much else you can do, because it's a supplier side fault more than anything else. If you come across it, as I was saying before, immediately report it. Your phone number in the UK is 105. There will be an equivalent in whatever country you're in, so have a look. And before doing any work on any TN installation, so TNS, TNC-S, anything like that, you should always check the current in the bonding cables and the main earth current with a non-contact current clamp. You can get ones that are designed for measuring leakage currents, which are much more sensitive. This one here is designed for obviously measuring like 600 amps. It's my one that I use for measuring current in tails and so on, but it will work to tell you if there's a significant current flow through the protective conductor. And obviously if there is, stop work immediately, don't touch it. But yeah, unfortunately there's not a huge amount we can do. With that being said, that's basically it. If you have any questions, stick them in the comments below, and I will see you in the next one. But hopefully this video was helpful for you, and yeah, I'll see you later. Bye.